Hello, everyone. Happy Pi Day. Today I'm even wearing my Pi Day t-shirt that says live every day like it's Pi Day. And I wanted to talk about an interesting connection about elliptic curves and pi, just for the sake of Pi Day. So here's one fact that is, I think, really interesting and that has a connection to pi and an explanation through elliptic curves. I think we know now enough about elliptic curves in the course on elliptic curves that you can actually understand like why this happens. So here is the fact that I'm interested in. Look at this number. It turns out that e to the pi times the square root of 163 is an integer. What? Well, let's see. So if you write the expansion of this number, this is 2625374126407 68743. So it's an integer. And of course, it's not an integer, but your calculator might think so because it's really close to an integer. It's this period and then 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 12 nines, and then 25, 0, 0, 7, 2, 5, etc. So it's really close to be an integer because there's like 12 nines here. And this cannot be coincidence that this happens. By the way, why do I know that this cannot possibly an integer? I know that this is not an integer because this is known to be a transcendental number. It is a transcendental number by a theorem of Gelfand and Schneider. So let me state that. So here are Gelfand and Schneider, who proved this actually independently in 1934. And the theorem says that if A and B are algebraic numbers, so if you have two algebraic numbers, A and B, A not 0 or 1, and B irrational, then any value of A to the B is a transcendental number. How does that apply to our case? Well, we had, remember, it was e to the pi times 163. And here, we can use the rules of exponents to write this as e to the I pi times I times 163, which is, this is just minus 1, to the 100 and minus 63. So A here is minus 1, and B is an irrational algebraic number, so it is transcendental. So definitely not an integer, but it's really close to an integer, like I wrote in the previous expression. Okay, so the fact that it's so close to an integer for a transcendental number, that's what's interesting about it. But there is an even more interesting explanation of why it is so close to an integer coming from elliptic curves. So here's the explanation. By the way, so here is a clue to the fact that elliptic curves and number theory, algebraic number theory is connected to this, is the appearance here, the mysterious appearance of the square root of minus 163. So we're going to use that. So let K be the quadratic field Q adjoin the square root of minus 163. And we are going to take a very particular elliptic curve. So I want to define an elliptic curve, which I'm going to call E163 if you want, and is given by the following Weierstrass equation. Y squared plus y equals x cubed minus 2174420x plus 1, 2, 3, 4, 1, 3, 6, 6, 9, 2. This elliptic curve. It turns out that this elliptic curve has extra endomorphism. So it's one of those special elliptic curves where the endomorphism ring is not just the integers, not just multiplication by n maps, there is something else. So it turns out that the endomorphism ring of this elliptic curve is special, is isomorphic to the ring of integers of k. Okay, which is, by the way, it's not just the integers that join the square root of minus 163. There's a little bit more. It's 1 plus the square root of minus 163 divided by 2. So the ring generated by z and that element. So we say that E has complex multiplication. Okay. Elliptic curve with complex multiplication have an interesting property, which is that we will see. We will not see in this class, but we'll talk about. Make this a little thinner. We will talk about potential good reduction later on in the class. But one fact of elliptic curves with CM is that that elliptic curve has potential good reduction at all primes. This has what this means is that for every prime of bad reduction, there is some extension where I can go up to, and over that extension, now the elliptic curve has good reduction at the primes above my prime P. Okay, so there is potential good reduction, so I can always go up in an extension to get rid of bad reduction primes, and this in particular has the consequence that there cannot be multiplicative primes, primes of bad reduction that is multiplicative. And what that means in particular is that elliptic curves with CM, not just this one, but any elliptic curve with complex multiplication has this property that the J invariant is actually an integer. Okay, this is proved in the second volume of Silverman in the Advanced Topics of Elliptic Curves. You can see a proof of that. So in this case, you can actually write it down, and the J invariant of our elliptic curve is definitely an integer, and it is minus 2, 6, 2, 5, 3, 7, 4, 1, 2, 6, 0, 7, 6, 8. 0, 0, 0. Okay. All right. This, by the way, if you want the factorization just for kicks, this is 2 to the 18, 3 to the 3, 5 to the 3 times 23 to the 3 times 29 to the 3. Interestingly, it's a cube. Okay. It's a perfect cube. All right. So we have the J invariant of the elliptic curve. And now, by the way, already notice this number, this big number, the J invariant it's very much related to the number we saw before. If I go back to the number, you see it starts with 2, 6, 2, 5, 3, 7, up to 0, 6, 8. So if you go back, you see 2, 6, 2, 5, 3, 7, up to 7, 6, 8, and then it differs in these 3 digits from that number, from e to the pi times the square root of 163. So it's pretty close. So now we are starting to get suspicious that this is really connected, of course, one thing with the other. So what is the connection? So the other thing that we know about elliptic curves, we've already seen, elliptic curves over the complex numbers are given by a quotient of the complex numbers by a lattice. So also, I have that my elliptic curve over the complex numbers, it is isomorphic to some complex torus, a flat torus, with the lattice being some lattice generated by 2 vectors, omega 1, omega 2, in the complex plane. Okay, and this lattice is unique up to homotheity. Okay, great. So what that means is that if it is unique up to homotheity, I can scale it, and I'm going to get the same elliptic curve over the complex numbers. So I can always actually write this will be E will be also isomorphic, or the same quotient will be isomorphic to the quotient if I do 1 times and the second vector just divide one by the other, or quotiented by the reciprocal. Okay, but one of those two vectors, one of those two complex numbers, has positive imaginary part. Okay, so I'm going to pick, there is one of these two numbers, one of the two is going to be element tau in the upper half complex plane. Okay, so the imaginary part is positive. So I can always suppose that C is given by 1 comma tau with tau in the upper half plane. Great. So in our case, actually, I know exactly what that is. So it turns out that for E163, the lattice over the complex numbers is 1 comma, and then the tau is 1 plus 100 and minus 63 over 2. Okay, where remember that that was the generator, those are the generators of the ring of integers of K. Okay, so remember that these generate over Z, they generate OK, with K being Q adjoint the square root of minus 163. Great, so I have the lattice. Now, what happens is that I can actually write for every elliptic curve, there will be a lattice, 1 tau, that gives me an isomorphism to my elliptic curve. And that tau is actually now unique. So for every tau, there is a lattice that gives them an elliptic curve. For every elliptic curve, there is a tau. So what that tells me is that I can actually give an expression of the J invariant that is the J invariant classifying elliptic curves up to isomorphism. I can give an expression of the J invariant in terms of tau itself. So, so one can give an expression for the J invariant of an elliptic curve in terms of tau, which is the tau that corresponds to the elliptic curve over the complex numbers, corresponds to the lattice 1 comma tau, and then that is the tau that you have to use there. Okay, and in fact, the expression only depends on what we call Q. It depends on Q, which is e to the 2 pi I tau. That's because there is another translation that one can do. If tau gives you an elliptic curve, then tau plus 1 gives you the same lattice because 1 is in the lattice itself. So there is the function, this function j tau is cyclic in that way. Okay, so it actually only depends on 2 pi I tau. Great. So I can actually give you what the expression of jq is. So jq as a variable of q is given by 1 over q plus 744 plus 196,884 q plus 214, 93760 q squared plus dot dot dot. You don't want to mess up these coefficients. These coefficients are actually very meaningful, and there's a whole other interpretation of these coefficients that goes into the world of monstrous moonshine and so on. So you don't want to mess up those coefficients. A lot of people will be upset if you do. Okay, so this is what's called the Q expansion of the J invariant. And now I can use the knowledge of my J, of my tau, in the case of the elliptic curve that I'm interested in, to actually write something about the J invariant. I know two things now. I know that the J invariant of my elliptic curve is an integer, and I know my tau. So I'm going to use those two things in our favor. So in our case, tau is 1 plus the square root of minus 163 over 2. So how much is Q? Q in our case is e to the pi I times 1 plus 100 minus 63. The 2 has canceled out with the 2 that was supposed to be in front of the pi. And I can now factor this as e to the pi I times e to the pi I times 100 minus 63, which is just minus e to the minus pi times 163, or minus 1 over e to the pi 100 square root of 163. And you see now that this is the number that we are interested in, right? So here we go. Now we have the number. This number, the reciprocal minus the reciprocal of our number, is this is very small. It's something like minus 3.809 times 10 to the minus 18. So very small. Okay. And that matters because then what happens, the J invariant of the elliptic curve, remember that we had an expression for it, is an integer, is approximately 1 over Q plus 744 with a very small error. Why? Because the next term in the Q expansion, remember, the next term would be plus 196,884 times Q. So the error is of size 10 to the minus 18 or something like that. So the error is, well, 10 to the minus 18 times this, which is a 6-digit figure, so about 10 to the minus 12. Okay, so with error 10 to the minus 12, this is more or less an equality with that error. Which, remember that there were 12 nines in a row in the expansion of our number here, shaded in green, to e to the pi square root of 163. So that's where that error comes from. So the error is about 10 to the minus 12. Okay, so but with that error now, I can then say that that 744 minus my J invariant, which I know it was minus, it started with 2, 6, and a lot of digits, is approximately minus 1 over Q, which is the number we were after. Pi times the square root of 163. Okay, so this is an integer, and this is of course an integer. So this is an integer. Okay, so the outcome of this is that e to the pi square root of 163 is an integer, up to an error of 10 to the minus 12, which is exactly what happened, which is what we saw that happened, that it was an integer, and then the expansion started with 12 nines. Okay, so that's it. And that's the explanation of why this power of e to the pi times the square root of 163 is very close to an integer, and the explanation comes from elliptic curves. And I hope this is at least one instance that motivates you to keep going later on after this class, which we will not get there, but after the first book of Silverman, start reading the second part of Silverman, or start reading about complex multiplication to understand some of the things that we've talked about here that lead to this fact. Okay, so that's it. All right, happy Pi Day, everyone. Bye.